continue this one. This will be the third lecture of nonlinear optics, am I right?
Yes. See time.
Okay. So we have been saying that laser is a kind of electronic instrument. It's an optoelectronic or a quantum electronic instrument because it became a quantum electronic instrument only from this. That's very important because before this one, harmonic generation, amplification, all those things were produced only the radio frequency or microwave frequency. Whereas in this case, it was found and it was shown that even at extreme high frequency, we should remember that extreme high frequency means it is extremely high. Why? Radio frequency usually means 10 power 6. Microwave frequency 10 power 9. Now look at all of a sudden, visible is 10 power 14. That means, let's say this is 15. Now the frequency has been shifted from here to here a million times. That means people could not believe that you can see here the change is 1,000 times. From here it is 1 million times. And then when it was shown that you could produce second harmonic in a high frequency like 10 power 15, it was totally surprising. It was a real quantum jump.
This is the frequency, doctor?
This is visible. 10 power 15.
Frequency?
Yes. All visible is somewhere around 10 power 15. You can calculate. It's around so many hertz. You see the developments goes in rapid pace. See, the radio frequency was the one done in 1880. Then this took 1910. And then look at it, this is 1960. And this experiment, if I remember, this 1967, second harmonic generation. It showed that you can get a harmonic generation in the visible region, and here once you get in one particular wavelength, then immediately it opened up a new, what is called Pandora box. Everybody wanted to jump in the nonlinear optics, try to generate frequencies. People did not. Okay, now what is important for us is this one. He did with the calcite crystal. Whereas in our equation, we never showed that anything about a crystal. We said a molecule or an atom undergoes vibration. If the vibration amplitude is very strong, it will go nonlinear. That's all we said. We never said anything about crystal. So this is, from our discussion so far, it is an atomic or a molecular phenomenon. From the discussion we had so far, nonlinear optical is an atomic are molecular phenomena. Molecular phenomena. That means if I take some suitable molecule and shine with a laser of omega, I should be able to get 2 omega. In fact, later you note down, I will show you a number of experiments. That is second harmonic generation with certain types of biomolecules. The easiest biomolecule that you are very familiar is your sugar powder. Bring sugar, we can produce second harmonic. Sugar. Not salt. Why?
Because ion.
Molecules and
Ion.
Salt is not a molecule.
That ion.
It becomes sodium and chloride. Whereas sugar is different. It's a biomolecule. In a biomolecule, asymmetry, you can pull the electron cloud here and there. In fact, we live because of this kind of biomolecule, because of this electron cloud can be pushed back and forth. I can give you one simple example. Later, it will be a big surprise. For 20 to 30 years, people were crazy about trying to get to the depth of biomolecule. You know certain biomolecule. Look at this one. I send a light. I take tube. It has nothing to do with the laser. Look at this one. I send light. I have sugar solution. Then, instead of sending ordinary light, if I take a polarized light, I send through sugar solution, and then the sugar solution will rotate the polarization like this. This is called optical activity, which was studied by Faraday for a long time. This is called optical rotation. That is, a plane of rotation is twisted by the sugar solution. Why? It means the sugar has some kind of sugar molecule, something capable of undergoing polarization, and the polarization leads to new charge cloud. New type of charge cloud, when they vibrate, produce light in this direction, not in this direction. It is called twisting. It's something like I drive a car. I have slush of water and mud. I go straight, but I go like this one. Okay. Up to this, people were not so fascinated. Then look at it. When I go drive a car, I can go this way or this way, right? Why should I go like this one? I may go this way or go. So if I have, look at this, if I have a place where there is water and mud, you come a car, you drive, sometime it goes. I come, sometime I go like this one, right? But it was found, strangely, that for certain type of molecule, it is always on the right side, not on the left side. Understand? This is what they could not understand. Then they selected what are the molecules which always twist in the right side. Okay? Then they found out, look at it, they found out all those molecules which are associated with the living system.
Right.
They have this kind of right type of twisting. Next step, you will be surprised. Another set of saying, if this is true, I will synthesize, understand? I will synthesize a certain type of molecule which always twists on the right side, okay? I will synthesize many of them, then put them in a box, put them in a glass vessel, okay? Put water, put oxygen, put lightning, put ultraviolet. Keep mixing. Is it possible to get a life out of that? You understand? You see the question. First see the step. I send a light, polarize the light.
The molecules will be live?
Huh?
The molecules will be live.
What is it? What is it?
Again,
Now go the step. Then you will see the importance of this one. I send a light. I send a polarized light, not necessarily laser.
Okay, I know.
Send it through sugar solution, ordinary sugar solution. Then the plane of polarization will be twisted like this. Okay. Sometime like this, sometime like this. Up to now, no problem. Instead of sugar solution, I take another solution like tryptophan. Tryptophan. Then this tryptophan will test right and left, but if you take ordinary tryptophan, you will see more often the light is twisted like this. You understand? That means when I drive a car, under identical condition, I may go this way, the road is ready. But I always go like this, more times here. That means there is something crazy associated with tryptophan. Okay. Then you try another biomolecule. Then it was found out most of the biomolecules twist the light only on the right side. Okay. Third step. Another set of scientists, particularly French scientists, they said, if this is true, I will synthesize a large number of biomolecules. You know saccharin? You know saccharin? Okay. You know diabetic?
Diabetic, yeah. Sugar.
Sugar. No. Sugar is bad. I cannot take this kind of sugar if I am diabetic. But instead of sugar, I can take small tablet, which are sometimes saccharin. There are so many of them. These are synthesized biomolecules. Understand? Small one. It will be having the same taste of sugar, but it is not calorific. So it will not give the problem of diabetics. These are synthesized biomolecules. You understand?
Now,
Now, come back to this one. If tryptophan is a biomolecule, if it produces right side rotation, not only tryptophan, I tried many, and then I found most of the biomolecules produce right rotation. This is called dextro rotation, D rotation. Dextro means right hand side always. Levo means left hand side. After that, people thought, if it is possible to synthesize similar biomolecule, understand? Then I put this biomolecule in a glass vessel, put light, heat, vitamin, ultraviolet, lightning, you keep on trying so many things. Then they expected all of a sudden from the biomolecules you will get a life. You see the big jump? You get the point?
we get live from
Life.
How is this true?
Listen, people thought and tried to experiment, and then there was one famous scientist, maybe Pasteur. You know Pasteur? He did an experiment and he found a life. Finally found out a bacteria. It was a big news for that year. But later it was found out that bacteria came from the water he has used. Understand? So there was no evidence for synthesis of life. So far. But it led to that kind of discovery. Okay. Coming back to this. Next time I will show you with the tryptophan you can get second harmonic generation. That means I am trying to show you that it is an essential molecular property, harmonic generation. But the point is this. Since the molecule is like this, randomly oriented, you will have harmonic generation, this. So it will be very inefficient way. Inefficient way of harmonic generation, Hg.
No way to improve this, doctor?
We are coming to that. Very inefficient way of harmonic generation. If we imagine the length over which harmonics can be produced, this is called LC. This is called coherence length. Coherence length. This is the distance through which harmonic generation is possible. In harmonic generation is possible in powder or randomized molecules. Molecules are randomly organized. Okay. Next system. In order to improve the efficiency of conversion of fundamental to the second harmonic, a lot of theoretical work was done, and I shall give you the summary of the theoretical work. It is like this. For any harmonic generation, you must say omega 2 is 2 omega 1. That is, this is equivalent to saying omega 1 plus omega 1 combined together omega 2. This represents energy conservation. How I can tell you now. The energy of a photon is always h cross omega. You know this?
Yes.
Okay. Now, multiply h cross. Then this represents energy of one photon plus one photon combining together, two photons combining together. Now this means two photons produce one photon of twice frequency. That's the meaning of this. That means total energy is conserved. If total energy is conserved, you must write down this equation like this. This is one step. Another one. Momentum should be conserved. Momentum must be conserved. That means K2 must be equal to 2K1. This is energy conservation. This is momentum conservation. What is K2? K2 is 2 pi by lambda 2. This should be equal to 2 times 2 pi by lambda 1. And then I shall expand 2 pi. Lambda 2 will be V2 by nu 2. This will be 2 times 2 pi V1 by nu 1. Because lambda 1 is a V1 by nu 1. Okay. Then you see I push it up. Look at it. It goes up. 2 pi u2 becomes 2 pi 2 nu 1 over v2 over v1, right? Then already we have shown 2 pi nu 2 2. This is 2 times 2 pi nu 1 is this. This is momentum energy conservation. See, look at this. This is omega 2. This is omega 1. This condition is satisfied. So automatically it means omega V1, V2 should be equal to V1. That is the velocity, or not velocity, speed of light of second harmonic should be equal to speed of light of fundamental harmonic, or fundamental first harmonic, because V2 becomes V1. You understand? Yes. If you remember the example I gave, it is easy. Imagine I walk at this step, okay? My little son also wants to walk with me. I hold his hand. Then look at it. By this, he must put twice the 2 steps, right? Then only I and he both will go together. That means he must come with the same velocity like me, but only thing is his frequency should be twice. That's the meaning of this. But this will not normally take place in ordinary material. This is not possible for ordinary material. Because for all material, if the frequency increases, refractive index also increases. We will call this, this represents refractive index. Refractive index. Now, refractive index is always V0 over V in medium. Keep this one. The V0 is the velocity or the speed of light in vacuum. This is the speed of light in a medium. For example, for glass this is 1.5. For this is 3 into 10 power 8. So, speed of light in glass will be only 2 into 10 power 8. The light goes slower in a medium of refractive index. From this point of view, as the frequency increases, refractive index increases. So it is like this. That means higher frequencies go slow. That's the meaning of this one. Higher frequency, that is light of higher frequency, travel slow. This is the nature of most of the material. Then next step is there are class of material, is called birefringent crystals. Birefringent crystals. Birefringent crystals, which have this refractive index. RA means refractive index, which have refractive index different in different direction. One such example is this. If I take a nickel prism, if I send the light like this, I send an unpolarized light, I put unpolarized light, then it will, from here onwards, one light will go like this, another light will go like this. The light that goes straight is called O ray, ordinary ray. The one that goes straight like this is called the extraordinary ray. Extraordinary ray.
Extraordinary.
This is ordinary. This is extraordinary.
It's in the light propagation in fiber optics.
No, that's totally different story. Fiber optics, look, you have fiber. I have another
Core and clad.
core and cap. Then I send the light, then you see the light will go. Since the refractive index is greater than this, it will undergo total internal reflection. This will be ordinary, it will not be extraordinary. Why do you say it's extraordinary? Why did you say it is extraordinary?
But some of the light go out of the gladding.
That is called evanescent.
Yeah, evanescent, yeah.
That's another story. That's evanescent means, you know what is you know what's the meaning of the evanescent?
No.
The word literally evanescent means, after Maghrib prayer, if you look at the sun in the west, you will see some little light.
Yeah.
Understand?
Yeah.
You will see some light.
Some light.
I mean, you can imagine you can go to Maghrib prayer,
Yeah,
come
I know.
out, you can walk around without light. You have some light.
Yes.
Such light is called evanescent light. Almost dying light.
Yeah.
Very weak light. Now, what is happening here is, since light can tunnel through this fiber, whatever is the light that is coming here, 95%, some 5% of the light is leaking out. That is called evanescent. That has nothing to do with this. And this has certain application later, but mostly it's a nuisance. For most of applications, in particular for fiber optical communication, this is a nuisance.
But I also read, Doctor, some of the light penetrate the gladding and come into the...
Yeah, that's what I'm saying. A little light goes and comes back.
Comes by, yeah.
It's all very weak. Very weak. That's a different story.
Yeah.
There is a reason for that. All the fibers that are used here are melted. You know, melted. It will be a liquid. It's a silicon liquid. And then slowly it cooled and pulled out. So there is no question of crystal behavior at all. all of them are amorphous. Whereas this is a crystal. It's a very good quality crystal. Only in crystal you have ordinary and extraordinary. In glass, ordinary glass, you know the difference between glass and crystal? What is a crystal? What's the difference? You know NaCl crystal. Where is NaCl? For salt.
So,
You take salt and you take glass. What's the difference between salt and this?
the arrangement of the molecules.
NaCl is an excellent crystal. Glass is not a crystal. We say it is a solid solution. That is, you melt it and allow it to cool. So, if you take water, there is no crystallinity. There is no particular this direction, all directions are same. This is not true here.
Okay.
Here, direction is important. The light that goes, one light goes like this, another light goes. This is extraordinary light and this is called ordinary light. Now this means the refractive index of ordinary light is not the function of theta. Whereas this one, refractive index of extraordinary light, is a function of theta. That's all it means. In some cases, in some crystals, the refractive index for extraordinary is greater than this. This is E is greater than O. These are called positive crystals. Another type of crystals, Ne is less than No. These are called negative crystals. These depend upon the nature of crystal. So now we must study a little about birefringent crystals. Birefringent crystals. This word refringent means refractive index. Bi means two. That is a crystal with the two refractive index. That's the meaning of this. We can give an example of a crystal called KDP, potassium dihydrogen phosphate. Potassium dihydrogen phosphate. KDP. The crystal structure for this is like this. If I send a light like this, one light will go, another light will go. This is O, this is E. Now, if I send like this, again this will go, it will split up. O, E. If I send this also, it is the same problem. Then they found out something funny about it. Look at this one. If I send the light, suppose I cut it, top and bottom cut it, send the light like this, when O and E go together. A direction in which O and E go together, this is called optic axis. Optic axis. Next step. Now, with respect to the optic axis, this is the optic axis. We will call it P. We don't want to put optic axis O, so you will get a confusion. Let me say this is the optic axis. It goes like this. So, now let me say, this is 0. I can define 2, x. This is y. Then, if I send, look at this one carefully. If I send the light at this angle, you will have 2 rays. Look at this one, you will have O and E. Out. So, this is O, this becomes E. Instead of this one, look at it. Just imagine, I send it like this. You will have O and you will have E like this. Then look at this one. This is the distance that E ray has to travel here. This is the distance E ray has to travel. Okay, that means the refractive index of E ray is a function of angle. Am I right? Okay, let me explain.
I understand, but what about O? It's the same.
O will have same refractive index in whatever is the angle. That is why it's called O ray.
Even the distance is different?
No, let's say refractive index. Refractive index always represents the speed. Okay?
Yes.
The refractive index of O ray is independent of angle. On the other hand, refractive index of E ray depends on the angle. Is it clear now?
Yes.
Right. Right, next step. This can be pictured in the following way. I can put a beautiful picture on this. Look at it. I draw an ellipse like this. This is optic axis P. This is perpendicular. Then if I represent refractive index as a function of angle, the refractive index should be a sphere like this. Why? This should be for O, this should be for E. Let me explain, then you will get the whole picture. Now once you understand...
Oh, the radius is constant.
Huh?
The radius is constant.
Radius is constant.
It's
The
the same.
speed is the same whether I send the light here or here or here or here.
Yes.
For O ray, it will be a sphere. So we will put the refractive index as a radius vector. On the other hand, for E ray, if I send this, refractive index is small. refractive index small means if I send the light in this direction, the E ray will go faster. Understand? This O ray will come slow. On the other hand, if I send this way, this is the property of this kind of crystal. Always the refractive index for E ray is less than the refractive index for O ray, but it keeps changing. Here it is too low, here it is same, here it is a little less. Understand? This is called negative crystal. On the other hand, let me represent a positive crystal. For a positive crystal, how will it look like? It will look like this is for O. Then look at it. This is E ray, this should be O ray, understand? I put E ray by this color, O ray white. Okay? In this case, the external ray is opposite of this, smaller than this one. Whereas in this case, small. So this is a negative crystal, this is a positive crystal. These are given in terms of the equation. You can write down this equation, look at this one. 1 over NE, refractive index of E ray equals cos square alpha over N1 square plus sin square alpha over N2 square. What is this N1 and N2? I can easily explain. This represents the component. This represents the refractive index of E ray in y-axis. You can call this N1. This is N2. Understand? N1 is N2 for O ray anywhere. For O ray, this and this same because it's a sphere.
For ordinary.
For ordinary. For E ray, here it is bigger than this. On the other hand, look at this one. For this crystal, this is smaller than this. Here, N1 is greater than N2. Here, N1 is less than N2. Because it is a sphere bulging like a stomach. This is bigger than this. Maybe the picture is not so good. I can put it like this. You see, now it's okay. You must look at this. This is N2.